And thank you for joining us. This is our March IGSPA Dig Deeper. We're thrilled to have Al Wallace as our speaker. Before we get started, I have just a few announcements that will get you up to date on what's happening at IGSPA, and we'll just go ahead and get started. First off, these town halls and Dig Deepers occur monthly. And if you go to the IGSPA website, igspa.org, you'll find an events and training menu at the top. That's where you'll find a form to submit any abstracts. We're still looking for some speakers for some of the town halls. We do have, or excuse me, some of the Dig Deepers. We do have all of the town halls filled for the rest of the year. But if you're interested in speaking, we have August, September, and October open for the Dig Deeper. Those are typically a little bit technical, more technical sessions. The town halls are a little bit broader type discussions. So check that out. We'd love to hear from you. Along those lines, we still have openings for sponsors for our town hall and Dig Deeper sessions. It's a great way to get your company name out there. And since these are recorded, your logo stays on that recording for as long as they're online, which we hope is a long time. An update on our conference in December. We're partnering again with National Groundwater Association, NGWA, and our conference this year is in Las Vegas, December 5th through the 7th. We do have registration open at the website. If you go to the igspa.org website, you'll find a button on the left-hand side that will take you to the conference information. We also have exhibitors set up for booths now, and sponsorship and advertising opportunities are ready to go. So check that out at the IGSPA website. You can see we have quite a few sponsors already. Our platinum sponsor for this year's conference is Climate Control Group. We have a gold sponsor already, Centennial Plastics, and two silver sponsors, Concord Engineering and Intertech Global. We still have quite a few available here. If you're looking at sponsoring the conference, check out the website. We have program advertising. IGSPA publishes a program guide for the conference that has a listing of all of the speakers as well as their bios and exhibitor information. So that's a nice opportunity to get your company recognized if you have an ad in the program guide. We haven't started putting our agenda together yet. We're still accepting abstracts for speakers until May 31st. If you go again to that same location, you'll find a form to submit an abstract. And at this point, you know, we have both our typical tracks, residential, commercial, loop installer, and we have an idea, a form or a choice on the form rather for an idea for a new track. So we're not limited to just those topics. If you have some ideas that IGSPA members would like to hear. We'll be making a decision on speakers in late June, early July, and making that announcement. We expect a full agenda again this year. And so if you would like to speak, make sure you submit your abstract just as soon as possible. As a business or corporate member, the directory is filling up. We get new members every month, and thank you very much for that. So if you haven't looked at our member directory lately, you're going to find a big upgrade. You can just click on the state or province, or if it's international, there's a listing, and that will take you to some details as far as those listed in that particular area. And you can search by, you know, whatever criteria you'd like to find a member that might be a great partner to work with. This is just an example of one of our members. You can see there's a lot of detail here, and that's available to business and corporate members. Just a reminder, if you'd like to get credit for this Dig Deeper webinar or our town hall webinars, in the chat message, if you would, please send your name and your email address, and we'll be collecting those. So this counts towards your renewals for certification, these town halls and Dig Deepers, as does the conference. Some housekeeping issues here. Make sure you mute if you would. And I'll be reading the questions at the end of Al's presentation if you put your questions in the chat. So if you could just put those in at any time during Al's presentation, and I'll read those questions, and we'll have some time at the end. We try to wrap up right at an hour, but Al has volunteered to stay later if you still have some questions. So we'll be around after 11:30 Central if we still have questions. We will be recording this session, and it'll be available in the next couple of days on the IGSPA website. There's a YouTube icon at the very top, and that's where you'll find the recording for this session. I do need to make you aware of our disclaimer and potential conflict of interest message. The upcoming presentation represents the opinion of the presenter and does not necessarily represent any official position, opinion, or endorsement of any products or services by IGSPA or its members. IGSPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. And with that, I'm pleased to announce our speaker, Al Wallace, President of Energy Environmental Corporation. Al, feel free to share your screen whenever that works for you. Al is the principal of Energy Environmental Corporation, or EEC, a service-disabled veteran-owned small business. Al's expertise lies in developing high-performance solutions for low and net zero energy buildings with a low carbon footprint. He has been awarded 5 U.S. patents for modular systems combining solar, geothermal, and radiant in-floor heating and cooling with reliable, simple-to-operate controls for superior comfort, indoor air quality, and energy efficiency. Al is a member of the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or ASHRAE, a certified geoexchange designer, CGD through IGSPA, CEM, certified energy manager by the Association of Energy Engineers, AEE, and a certified trainer and installer for IGSPA. He earned a Bachelor of Science degree in Aeronautical Engineering from the U.S. Air Force Academy in Colorado Springs, a master's degree in Business Administration from Golden State University in California, and dual master's degrees in architecture and landscape architecture with certificates in design build and historic preservation from the University of Colorado at Denver. So we're thrilled to have Al with us today. And with that, I turn it over to you. Thank you very much.
Jeff, thank you. Can you hear me okay?
Can hear you fine, Al.
Perfectly, thanks. Appreciate your leadership at IGSPA. It's a great organization, been a member for over 20 years and keeps us all on track. And I think these are really exciting times. Before I get started, I want to let you know that many of you have put in the text messages your email to get a copy of this presentation. On the last slide, there is a link where you can actually just download it on your own, so it'll save you some time to do that. I will tell you that the slides are designed to be a reference moving forward. Normally, when you do a presentation, you just show a bullet and you don't explain anything. That's the responsibility of the speaker. I took the approach like I did at the IGSPA conference where we presented this to provide a reference for you. So there's going to be a lot more information on the slides than I actually talk about, but the detail is on the slide if you want to refer to it later. As far as disclosing conflicts of interest, we are a commercial rep for systems design and consulting for net zero energy buildings. That'll become obvious in the presentation because we have several patents on this technology. And it allows you to get between a 50 to 70% energy savings on a building to implement it, which gets you very close to net zero with standards that I'll talk about. I'll tell you my background was as a fighter pilot, so I'm kind of keep it simple, stupid. When you push the stick forward, the houses get big, and you pull it back, the houses get small. And if we can't explain technology in those terms, then we really should be in a different business. Because that's what we need to get the word out. Because there's a wide audience from engineers to architects to installers to drillers, I've kind of taken the least common denominator approach, and I explain some things like heat transfer that may be obvious to some of you, but maybe not the others, so that we're on the same baseline. So net zero is an ambiguous term, but essentially it means that the building produces more energy through on-site generation or other sources than it actually uses. On the left is the newest building at the Air Force Academy, uses radiant floor cooling. That's my alma mater. On the right is 200 years of tradition unhampered by progress, the West Point Military Academy. Davis Hall is actually using the technologies as talked about in this presentation. So the question really becomes, what is a net zero architecture and what are the goals? Technically, you can make any building, you can make a 1950s warehouse with really crappy equipment and at net zero by putting a 5 million kilowatt solar array in the backyard, but that's not the goal. The goal is first to provide comfort and indoor air quality at an affordable cost. If you can't show that it works on the pro forma, then you're basically wasting your time, because that is where in the commercial realm, people are working, even though you might want to save the planet or build green. If it doesn't make sense financially, then you're basically challenged. I spent 15 years in the .coms with Oracle and Sybase. And at the time, you had a dedicated workstation that talked to a dedicated server. We did not have what we have today, the internet, where any client can talk to any server. But if you imagine that for a building where we can take hot or cold from any source in the building and move it to any other source where it's needed most efficiently for heating, cooling, and dehumidification, that's the goal of the architecture that I'm going to present today, that it actually achieves that. You also want to enable net zero capability. Most buildings that are code compliant have an energy use intensity of around 100 to 200. Net zero buildings tend to be under 50. And the example that we have worked on recently in Denver here is a building that's 200,000 square feet. But essentially, if you're calculating net zero, if you have an EUI of 26,000 BTUs per square foot per year, you basically need a 600 kilowatt solar array for every 100,000 square feet of building. So a 600 kilowatt array would generate 761 kilowatts a year for offsetting energy use. And that's going to get you close to net zero. And I don't want to exclude any hybrid systems where you might want to use a boiler for peak loads, or you might pull in a cooling tower with a hybrid system with a ground heat pump. But I do want to suggest that one of the goals here is to minimize water use. And that's an advantage of geothermal over, say, using a cooling tower. With the exception of the cost of drilling, it allows us to run year round without using water. We want to minimize carbon emissions, and both carbon emissions and greenhouse gases assumes you have a clean grid. Here in Colorado, we have people plugging in their Teslas, arguing that it's green, but we have a coal-fired power plant in Boulder that actually is powering up those Teslas. So it's a bit of a challenge. If you have on-site generation with whether it's hydro PV or any type of energy production, you want to minimize your carbon emissions, which is not burning fossil fuels, biofuels, or biomass. Whatever you say in front of bio doesn't necessarily make it not carbon emitting, even though there's arguments for no carbon emissions when you burn wood chips from beetle kill pine. I don't buy into that argument, but I'm basically saying you don't want the carbon emissions, not whether it affects the impact of the environment, but it also creates combustion fumes. And that's one thing we want to avoid with greenhouse gas emissions is methane, carbon dioxide. And as we're seeing in the heat pump industry, moving to different refrigerants that might contribute to greenhouse gas emissions. This is the format of the presentation. I'm very quickly cover building science, how heat moves and how that is affected. And it actually breaks a paradigm. When you're used to forced air systems and you start looking at radiant hydronic systems, they act fundamentally different. And one of the big differences is how heat gets transferred and how you get thermal comfort under ASHRAE standards. I'll then cover net zero energy building fundamentals. And these are, if you're going to make a checklist of 5 things or so that you want to see in a net zero building, I would suggest that half of all net zero buildings today in the US are using this technology, and perhaps 70% of them in Europe are using this technology. And the first thing is you're using hydronic distribution instead of forced air for your primary heating and cooling. You have a high performance building envelope, which is high mass versus low mass, and I'll define those later. And another key element is separating ventilation from heating and cooling. There's a book by Kyle Moe. It's called Thermally Conductive Structures in Architecture. It's not in print anymore, but it covered buildings from the 1990s and 2000 that were high thermal mass radiant applications, and they separated heating and cooling. So your ductwork and your forced air loads are not based on your heating and cooling load. It's simply based on your ventilation requirements and supplemental cooling. What that means for a residence is that instead of exposed ductwork or chases, it gives an architect the flexibility of designing clean open spaces where you're running your ventilation and cooling ducts between floors, between the ceiling and the floor, or underfloor air distribution system in commercial buildings, and you don't have massive ductwork to blow air. You'll use a DOAS. We'll describe what a DOAS is, but you have a centralized ventilation and humidity control system, which is energy efficient. And just like the .coms, we have interoperable systems architecture. Whether you want to use a boiler, a solar thermal array, a geothermal heat pump, excess heat from a data center, this architecture integrates all the heating and cooling sources and then controls it with predictive controls, which we'll define in detail. An optimized heating and cooling system has specific configuration to optimize performance. I'll first talk about what our requirements are. Basically, it's triple bottom line: people, planet, and profits. Look at traditional forced air heating and cooling systems that are low energy. You can reduce energy significantly with say a geothermal heat pump system, but you're not going to get into the realm of net zero unless you do some of the things that we talk about in this presentation. Hydronic and heating cooling technologies are pretty mature, and I'm going to show you how you can actually use water to heat or cool even by blowing air through a fan coil. And we'll show you some modular radiant panels that we developed that now GeoFlow is making in Indiana, and they really simplify complex geothermal with hydronic radiant systems when you're implementing them. On the source side, meaning the source of heating or cooling, configuring heat pumps where you're not optimizing the COP, but you're optimizing the system performance factor, which is the overall system. So I'm doing pumping energy, considering thermal mass. If I calculated the total power of the system and divided the output of the system by that, I get a significantly different seasonal performance factor. And I'm going to show you how you can get a COP as high as 50. That's 50 versus say 3.5 to 4 that you typically get with a ground source heat pump. And then we're going to talk a little bit about how variable speed systems affect this. That could be pumps, fans, or variable speed compressors on heat pumps. And I'll finish up with predictive controls that are used in most of these buildings, and then give you a diagram of what this looks like as an architecture put all together. And I'll talk about some of the patent technologies. If you actually looked up our patents on Google Patents, you could actually read 20 pages of technical detail that would cover the content of this presentation. And that goes back to 2012 timeframe, but it's applicable today. For building science 101, I want to talk about heat transfer. There's 3 ways that heat gets transferred within a building: conduction, convection, and radiation. If you look at a forced air system, it's primarily convection. There may be a little bit of conduction once it warms up surfaces, but you're essentially moving air at a certain temperature. And the greatest heating load on a building is the radiation that comes from the sun. If you think about shortwave radiation, that's the stuff that causes sunburn. So if you have light shining on you that feels uncomfortable when you're not in the shade, that would be shortwave radiation. And as you can see in this building graphic, the purple dotted lines is long wave radiation. So when shortwave radiation hits a space, it starts to warm up the space, or we call that mean radiant temperature of the surfaces, the walls, ceilings, floors, and it bounces all around and it causes the building to heat. In a forced air system, what we do is we think about cooling as cooling a space, which is in fact cooling a space that we allowed to overheat. That's fundamentally different from a radiant system that primarily works with conduction and then also radiation for heating and cooling, where when the shortwave radiation hits the building or this cooled surface, it instantly absorbs that radiation and does not allow it to warm up the space. The analogy I use is a cathedral in Europe. If it's 60 degrees overnight and the doors and windows are open and you have 50 tons of concrete that have cooled off over time, when the sun comes up the next morning and it's 90 degrees outside, that building is still comfortable and cool because it was never allowed to heat up. And then conduction is resistance to heat transfer, or R value is resistant to heat transfer, which is through conduction, which would be, your 120-degree attic. You have higher value insulation up there to protect you from the intense heating load if you're in a cooling environment. And you have doors and windows, et cetera, and you're familiar with that. So if we look at ASHRAE standard 55, which is a comfort standard, they identify 6 factors for comfort and how to measure those. The 2 on the left are factors related to human occupancy. Metabolic rate, a lot different heating and cooling comfort if you are in an exercise room in your yoga studio versus you're in a retired citizen's home and they're reading magazines laying in couches. We can't really control that with heating and cooling systems, but the 4 factors on the right, airspeed, air temperature, humidity, and radiant temperature, we do control with heating and cooling systems. And forced air systems only control airspeed and air temperature. So they're significantly less comfortable, despite what arguments you might make. When you have a supply grill on heating mode with, say, 100-degree air, somewhere in the room at 72 degrees, and then it returns to 68 degrees back to a furnace or a heat pump. That's not as comfortable as a radiant floor or ceiling system, which every single square foot of that entire thermal mass is a heating or cooling sink or source. And then in this example, if you are going to do radiant cooling, it actually minimizes the bouncing around of the dotted purple lines. And you can see in this graphic that as the radiation comes in, it's absorbed by the cooled surfaces before it heats up. And then if the system is in cooling mode and you have somebody with 98-degree body temperature, you're actually radiating to the floor because the floor is 68 or 70 degrees. And so to you, it feels cool. Just like in the wintertime, if you're against a cold window, it's not drafty, it just feels cold because you're radiating to that cold window and it feels like there's a draft in the room. Our other focus is to focus on moving water versus air. This is another way of explaining geothermal to clients. Those that have been in the business for a while, you basically explain how an air conditioner with geothermal uses 55-degree groundwater for heat transfer, and water is a better heat transfer medium than air. This is the first slide where I'll explain. I'm not apologizing for it, but there's a lot of detail on this slide I'm not going to talk about relating to kilowatts, watts, BTUs, and calculations that we'll use. But if you want to refer to this later, then you can actually read it in detail. But on the left is a 24-inch diameter duct. And if you do the math, there's 100,000 BTUs per hour that I can deliver with a fan. And on the right, it's a 1.5-inch diameter pipe. The pumping energy is 43% less for pumping water than it is for blowing air for the same amount of energy. And that's a fundamental thermodynamic principle. Just like the water-cooled engine on a car is more efficient than air-cooled, and using a ground heat exchanger with water transferring to your condenser is more efficient than having an outside air coil with an air conditioner. This is an example of a high performance building envelope. On the right is your low mass forced air system. You can see how the complexity of that slide, the slide isn't not intended to be read, rather it simply shows you the complexity of ducted systems, especially if you try to do zoning. And then the core and shell, you have steel frames with lightweight infill and large ducts for forced air, complex zoning, and you have significantly different temperature variations within the space versus on the left, a high mass radiant system. First, the floor system is significantly different. On the little blue graphic, the second one from the left, you can see the raised floor, which is an underfloor air distribution system, and to the right where I have ceiling floor. Those are radiant surfaces, which is another system with or without underfloor air distribution, but it's greatly simplified. And then in plan view at the graphic at the far left, you can see that a thermally conductive structure, or we use TCS as an abbreviation, that thermally conductive structure is easily zoned by using a zoning system with zone valves. So every single room and every space that you want can be zoned to have its own heating and cooling within the system. It's minimized ductworks, it's simplified hydronic piping, and it's also smaller temperature variations in the space. Here's an example at Fort Carson on a project I worked on a couple years ago that's radiant floor cooling for the 13th Combat Aviation Brigade. And you can see them putting the tubing on the floor. And in this 440,000 square foot building is 10,000 gallons of circulating fluid. So when I talk about thermal mass, I'm not only talking about the thermal mass of the concrete, but when you have 10,000 gallons of fluid in circulation, you can do the math on that, on its ability to dampen temperature variations between spaces, but also within a space. After we think about heating and cooling as being separate, we have to think about ventilation. And the easiest way is simply open a window, which is not necessarily the best thing to do. There's a radiant floor cooled building in Pittsburgh that has some really serious problems because they have operable windows, and high humidity, it would cause condensation. So if anybody opens a window and it gets humidity in the space, they have to shut down their radiant cooling system, which is not really conducive to employee happiness, comfort, etc. A variable air velocity system is a constant temperature airflow for larger buildings. It's at a, variable airflow at constant temperature to normalize the space, whether it's conditioning or supplemental cooling. For residences, you need a heat recovery ventilator, HRV, or energy recovery. The difference is that an HRV just does sensible heating. So in the wintertime, the cold air comes in and is pre-warmed by the stale air going out. An energy recovery ventilator has the ability to do latent heat recovery, which is moisture control. So it maintains humidity on both sides as well, using an enthalpy wheel, desiccant wheel, or something for that. A dedicated outdoor air system is basically a commercial ERV that's variable speed, and then it has fan coils for heating or cooling the air. If you want to dehumidify, but you don't want to cool, it actually has a cold coil that you have below dew point. The water condenses, and then it's reheated to go through the unit to give you drier air. If you want to heat it, you just simply turn on the heating coil. And if you want to cool it, you just turn on the cooling coil. And those coils can be refrigerant coils, and that could be a typical vapor compression air source heat pump, like an air conditioner coil, or it could be a geothermal heat pump with ground source, or it could be hydronics. If we think about making hot and cold water super efficiently, then the best option throughout the building to eliminate ductwork distribution and the cost of that, as well as discrete control within zones, you basically can use distribution of the cold or hot water to meet requirements like this to heat or cool the coil. If you're doing radiant floor cooling, a critical issue is dew point control. I hear engineers tell me that I don't want to do that because there have been so many lawsuits over radiant cooling. I agree with that. I think there's been more lawsuits over radiant cooling than any other technology that I've looked at in 20 years. And it's a simple problem to solve. I would use the analogy, if you undersize your ground loop for a heat pump, somebody's going to get in trouble. The first summer that thing overheats, or the first winter where it freezes up, it's on the contractor or the designer because they did not consider or calculate the demand of the heat pump or the cooling and heating loads correctly. And the same thing goes to dew point. If you calculate the dew point, and here's a psychometric chart, even heating and cooling engineers are pained by this when they take their EIT test. You go into the chart at the bottom with the temperature, and then you go vertically to a chart with the humidity, and then you go laterally to the upper left to find your dew point. In this case, 68-degree floor temperature in a slab relates to a dew point of 56.5 degrees at the floor. That's important to note because if I now circulate 58-degree water, or I keep the floor above 56.5 degrees, I can never get condensation. So condensation control is very straightforward, but the complexity comes into play. Where do you actually measure the temperature? And this comes to play in the example where I show a chilled beam. A chilled beam is basically a fan coil on the ceiling that has cold water, or it uses natural convection, and I'll show some pictures of that. On the bottom right, those that you design ground loops know the Reynolds number, you want above 2,500 for your ground loop to ensure you have turbulent flow, which is good heat transfer. For a building with forced air or a building that uses radiant cooling, if you think about having a ceiling fan, which is blowing air throughout the space, you create turbulent flow and you don't get the stratification that you see in the upper right, where the floor is 68, somewhere in the middle, it's comfortable at 72, 73, and then the ceiling's at 80. If I measure the temperature at the floor and I circulate the water at the chilled beam, so the chilled beam's at 80 degrees and I go to the 50% humidity, now my dew point's 66.5 degrees. And if I circulated 58-degree water, then water would be dripping off that fan coil onto the occupants, and that would be not very fun for the designer or the occupants. So you need to really think about where you measure dew point, where there's condensation, and how you control humidity in the space. And ultimately, you're trying to achieve comfort. That's uniform temperature and humidity. That's where a forced air system is not that good at controlling humidity. And high humidity environments and with variable speed heat pumps, we'll talk about that, where they have the ability to control humidity by varying fan speed and compressor speed. But ideally, you want to keep the humidity between 40 and 50%. That's really challenging in a place like Colorado, where the average humidity in the house or a commercial building would be 20 to 30%. So you may or may not have to dehumidify, but that's the target range. And then a well-insulated tight building is going to be more comfortable than one that's leaky, because you can control that. Indoor climates related to fresh air ventilation, we're going to talk about that. If you have a filter like MERV 11 in your DOAS unit or your heat pumps, you basically are lowering the allergens. And with COVID, we found that higher ventilation rates actually cause healthier environments. And ASHRAE's kind of gone back to the drawing board on their ventilation recommendations. And as we talked about dew point, you have to control dew point so you don't get condensation on the radiant surfaces. On the environmental side, we think about total energy use, but I would argue that the highest cost savings on energy is reducing peak demand. Peak demand charges in many cases exceed the actual electrical usage charges. And if you think about rolling blackouts in Southern California at 1 or 2 in the afternoon when all the air conditioners are running, if you have a low mass building, you're going to have to cool that space at the highest demand. If you have a high mass building that has 50 tons of concrete that's already cooled, you can pre-cool that space at 10 o'clock in the morning, and it'll float you through 3 or 4 hours of that high demand requirement for your heat pumps and other equipment. We're focused on carbon emissions and greenhouse gas, which I talked about. And then on value, we're not only talking about efficiency, but reduced maintenance costs. You'll find that radiant hydronic systems with pumps are easier to maintain, and you don't have the issues with maintaining water in a cooling tower or maintaining fans on an outdoor roof. Most of the pumps are indoors. And as we're seeing today, triple bottom line, which is private people and planet, is a criteria to meet. So here's some traditional system that's kind of an overview baseline, but a forced air furnace with air conditioning outside. An air conditioner is an air source heat pump. I actually had an engineer at a client tell me that a chiller was not a heat pump, when in fact it is, and I'll show you the picture. But an air conditioner is an air source heat pump that's cooling only. If it's reversible, we now have a heating or cooling air source heat pumps. Even though they have cold temperature versions of these, on commercial buildings, when you get below 25 or 30 degrees, the efficiency is so low when the outdoor air temperature is that cold that they're not very efficient. Or when it's super hot outside, you have the reverse problem. And these are controlled with a basic thermostat. The only reason I bring this out is that this is a 24-volt control system for a residence. When you get to commercial buildings, we now have to look at direct digital control systems. So your typical Honeywell thermostat doesn't work in those environments. But at the same time, this thermostat's pre-programmed. There's not a lot of algorithm control that you can do. And that's one of the challenges we face today with radiant floor cooling or radiant ceiling cooling, is that the control system is complicated and there's no off-the-shelf controls. So a boiler, as you see in a commercial buildings, takes about the space of a car garage bay. For a commercial unit, it's the size of a trash compactor. 2 feet by 3 feet by 1 foot in a residence, but essentially burns fossil fuel or wood or biomass, whatever you want to call it, oil, and it makes hot water. On the right is a chiller, and the chiller is an air source heat pump, or I should say, it's a water to water heat pump that uses cooling from a cooling tower, which is air that's evaporated. So water is circulated either through a heat exchanger or in a closed loop or directly through that cooling tower. That can lead to all kinds of problems. Not only are you using 1 gallon per ton per minute, but you're also subject to Legionella and some other stuff in the cooling tower if you don't maintain it. And that's been a big issue, is maintaining not only the chemical balance in cooling towers, which is extremely costly, but also maintaining it for health and safety reasons. The heat pump cannot move heat from one side to the other. So you can't make chilled water unless you have somewhere to dump the heat on the source side. So when we're switching gears to how things get distributed, this is a graphic of a radiant heating system that you would be familiar with. This is low mass. You can see that I don't have concrete holding the tubing and the floor on the bottom. But the key element here is that I'm circulating hot water from a boiler or some other hot source through the radiant system. And as each zone needs heating or cooling, or heating in this case, a zone valve opens, it meets the response time, the temperature turns off the zone valve, and it starts all over again. The efficiency of this system is not only the pumping energy as compared to forced air, but more importantly, how the hot water gets made. If I have hot water being made by a heat pump, then the efficiency is 3.5. If I'm using a boiler, as in this graphic, and I derate it for altitude, say in Denver, Colorado, it's 85% efficient, or a COP of 0.85. COP is the power out that you get from the system based on power in. And as those of you know in the heat pump industry, it's around 3.5 for a heat pump. For combustion appliances, it's less than 1. And for all electric appliances, like an electric hot water tank or electric furnace, by definition, it's 1.0. Another way of distributing hydronic water, hot or cold, is through a fan coil unit. So the coil on the right, the upper part of that has water pipes that circulate through a heat exchanger. And then there's a fan that blows it through the hot air or cold air. And the only control parameter in this system is the radiant supply temperature. And that differs from radiant cooling, which is the next slide, where I need to make cold water. Well, if I'm using a chiller, since there's no combustible appliance that makes cold water directly, I either use a source of cold water from a cold lake or cold water source, or I have to chill it to temperature. And now that you introduce a heat pump, you have to have thermal storage. Unlike a boiler, you can't just do a single pass through a heat pump through a heat exchanger and not have that heat pump lock out. Thermal storage that's recommended by most manufacturers, whether it's residential or commercial, is about 1 gallon per 1,000 BTUs. So a 5-ton system, which is 60,000 BTUs, would require 60 gallons of thermal storage. That doesn't have to be a tank. As I mentioned with the picture below with the Fort Carson Barracks, they have 10,000 gallons of water in circulation. So as long as that water in circulation can be accessed by that heat pump, it provides that buffer that you need to prevent short cycling. But in this cooling application, I'm circulating chilled water in the floor. And so I do have a control parameter of the thermally conductive structure temperature, but I also have to measure the space temperature and the space humidity. The way of distributing chilled water systems is by the graphic at the bottom, or it's through a fan coil to the right of that, or what's called chilled beams. An active chilled beam is a fan coil built into a cool heat exchanger on the ceiling. A passive chilled beam is natural convection with the same chilled beam. And if you have condensation on that beam, you have to have condensation control, which gets very expensive with condensate drains, et cetera, and also is poor for aesthetics. Usually what they'll do is, if they're going to provide supplemental cooling from the ceiling, they'll use a passive chilled beam. And just like the radiant floor, they'll keep that chilled beam above dew point to make sure you don't get condensation. Another factor when you consider radiant cooling applications, which is not so much with forced air, is how much solar gain you get. With a forced air system, we calculate solar gain and we say, okay, there's 40 BTUs per square feet of solar heating load. Like in the Los Angeles Federal Building, they use radiant floor cooling in the lobby only, because radiant cooled floors are like kryptonite to shortwave radiation. When it hits that floor, it does not bounce off. It gets immediately absorbed by the floor just because of the temperature differential and the thermal interaction of the floor with that radiation. So with direct solar gain, the capacity of a radiant floor is 25 to 32 BTUs per hour per square foot. If you don't have direct solar gain, it's 8 to 12 BTUs per hour per square foot. And this is probably the #1 area that engineers get themselves in trouble with radiant systems. Manufacturers do not produce good data for actual radiant floor capability. Pacific Northwest Labs is doing a lot of research on this. They recently got a $14 million grant to figure out some of this stuff and provide better energy modeling. But if you use the 8 to 12 BTUs per hour per square foot, you'll never get in trouble because you calculate a supplemental cooling load using heat pumps, fan coils, or whatever to pick up the balance of the load. And if the radiant floor outperforms your 8 to 12, it just outperforms it and you use less supplemental cooling. If you have a two-sided fan coil that's exposed to air, the top of the coil and the bottom at the ceiling, you can get as high as 25 to 50 BTUs per hour per square foot. And that's specific to solar applications. And solar could also be heating loads from light. So if you have high occupancy with high lights, that would be a situation where you may want to control, we talk about later with algorithms, pre-cooling the building before it's occupied if there's a high heating infrared load. This panel is one that our company actually built over time, and we refined it to make basically 24 zones fit on a 4x8 HDPE panel. We showed this as the IXPA show like 5 or 6 years ago. What's really exciting for me is that GeoFlow is now manufacturing this panel, because with hydronic contractors, it's really hard to stay up to speed on all the different parts and pieces that go into it. It's kind of like a radiant panel in a box where you hook up the tubes for your radiant circuits at the top. You hook up your hot or cold water source, either from tank or hot storage or cold storage. And then the panel does everything else for you. It's got a built-in variable speed circulator. It's got injection pumps to inject the tubing. It do hot or cold. It has 3-way mixing. It's got all the stuff you need for flushing it out. And I think this is going to greatly accelerate implementation, whether it's a residence that's 10,000 square feet or less per panel, or a commercial building. If I have a building that's a 20,000 square foot footprint, I can put 2 of these panels per floor, and it doesn't matter how many floors the building is. It greatly simplifies distribution to that entire floor. So all you have to do is put the panel on the wall in a mechanical room on that floor, and then hook up hot or cold water. And essentially the controls pre-wire the zone valves to inputs, whether they're 24-volt AC, or as in a DDC system, you'd use closed contacts, where the DDC system says open zone #1, and the panel would actually do what you needed to do. So this is pretty exciting, and GeoFlow is one of the biggest manufacturers of the flow centers in the US right now for you guys. So they're a reliable manufacturer. So let's switch over to the heat pump side and see what the efficiency of a heat pump is. So on the source side for heating, we basically have a traditional heat pump with a ground loop that could be vertical, horizontal. And horizontal, I include solar patios, which would think about snow melt in a parking lot. So if I'm going snow melt in a parking lot in Colorado, like today, that parking lot is going to get up to 100, 110 degrees. And tonight, when I need warm water for the building, if that water is above my heating set point, I can use the fluids directly and we'll get to that. Or I can provide my heat pump with warmer water than the ground loop. That saves heat extraction from the ground loop and also makes the heat pump a lot more efficient. It's those little efficiency gains that get you to the net zero goal. Other types of ground heat exchanges is an open body of water, or Denver Water headquarters here in Denver uses a potable water conduit. So they serve 1.5 million clients, and they have their heat exchanger hooked up to potable water conduit. So that provides all their cooling for free without using a heat pump. But in this case, you only count the useful heating and cooling. So if I have 3.5 units of heating and the heat pump uses 1 unit of power, my COP is 3.5. The same thing in cooling, the COP is 3.5 because I'm rejecting heat to the ground or taking it out of the ground. If I want to improve the efficiency of the heat pump, which I kind of touched on, A heat pump is more efficient in heating mode with hotter source water, and it's more efficient in cooling mode with colder source water. So if I'm in the middle of the summertime and I have 55-degree water in the ground, let's say in April in Colorado, that's going to be more efficient than August or September where the ground is heated up to 75 degrees. So if I have the ability to have any type of heating or cooling system talking to my sources, I can move heat from any requirement to any source pretty easily if I have the architecture that does that. So if I have solar thermal arrays, that's heated water. It might not be superheated, but it may be hotter than groundwater, and I can offset water that way. There's a cooling tower, which kind of talked about with chillers, and a big use is data centers for ejected heat. I will warn you that a data center for an office building is different than a data center, say, for Google, where you have square miles of data centers and computers using millions and millions of BTUs of cooling. Most data centers for an office building would have a lot lower cooling load than you would need to actually heat the building. So if I was using a chiller to heat the building, if I was heating the building with a heat pump using data center rejected heat, I might have 6 tons of capacity out of the data center, but I need 40 or 50 tons out of the building. So that's just a warning. You have to calculate data centers. They don't inherently provide you unlimited heating as rejected heat. The other alternative is using air source heat pump. We're seeing in moderate climates, an air source heat pump to make hotter chilled water is a reasonable alternative. They're starting to come out with cold weather or cold climate heat pumps. That's a yet to be determined. It basically gives you a bigger operating range, but it still doesn't have the efficiency of geothermal. If I want to double my COP, I can get rid of the ground loop. Here's an example where the heat pump is put between a cold storage and a hot storage. So let's imagine a cold tank and hot tank for a minute. The heat pump makes the cold tank cold by sucking heat out of it and putting it into the hot thermal storage. In this case, the COP is 7.0 because I'm getting 3.5 units of chilled water and 3.5 units of hot water using a heat pump in the middle without the cost of a ground loop. An application I worked on in Aspen, Colorado, is a hotel about 10 years ago that had a constant 6-ton cooling load, even in the middle of January when it's 20 degrees outside. In the summertime, they might have had a 50 or 60-ton cooling load, but the point was year-round at a 6-ton cooling load, and year-round their heating load was far greater than that. So we put a heat pump between their cold water loop and their hot water loop and let it run 24/7. And it paid for itself in 18 months in the BTUs that it created. And it's because you get such high COP and you don't have the added expense of a ground loop. This was simply tapping into the cold water supply and hot water supply in a mechanical room and putting a heat pump in the middle. The highest efficiency is when you directly use fluids for heating and cooling. If you look at groundwater at 55 degrees and a radiant floor requirement in cooling mode of 58 degrees, if I just take the groundwater and circulate it in the floor, I'm using one pump, which is 200 watts an hour, like a Magna 3, circulating fluid to an injection closely spaced T's on the radiant circuit, which is circulating water through the radiant system. I'm using 400 watts an hour, and I'm generating 72,000 BTUs per hour. So I'm using 400 watts to generate 6 tons of cooling, and my coefficient of performance is 53. On my house, I do this, and it works for May, June, July, but then the ground loop gets too warm, and at some point, I have to turn on a heat pump to chill the cold side. But for 3 months, I'm essentially getting free cooling. The example I use for Denver Water is they have a potable water conduit, so they can do this all year long because it's basically an open loop system on the other side of the heat exchanger, and they never technically heat up the ground because they're using a source of water in that. So when we now talk about thermal storage versus thermal energy storage, as I touched on before, the high mass structure itself and the tons of concrete is your thermal storage, and the thermal storage with water circulating to the heat pump dampens the diurnal temperatures between night and day within a space. So one is for radiant high mass systems, you don't set them back to 55 degrees or 60 degrees at night because it takes a long time to recover. And tests have shown that setting back a system like that doesn't necessarily save that much energy, but is problematic whenever the system doesn't respond as quickly or the weather changes faster than you thought. And now you have to provide supplemental heating and cooling. Thermal energy storage is what we think about with rock beds or tanks of water, and there's a company that sells TES tanks. But if you think about it, ground heat exchange is your best source of having a thermal energy storage system. You can actually position it as that. Let's think of a scenario where you have a solar thermal panel, and the biggest challenge for solar thermal is in the summertime, we generate far more heat with the panel, and you need tanks of water to handle that volume so you don't turn everything to steam. In Colorado, our cooling load is 60% of our heating load for residences. And let's look at a building that has a 10-ton heating load. It would have a 6-ton cooling load. If I separated the ground loop to a 4-ton ground loop and a 6-ton ground loop, I could actually use a 6-ton for cooling in the summertime and the 4-ton to absorb extra heat from the solar panels, which supercharges the ground loop when I turn into heating mode in the fall. But it also allows me to undersize the solar storage I need for the solar panels so that when they're working at optimal efficiency in the fall, the winter, and the spring, I'm not overheating the system in the summertime. Now let's switch gears to variable speed devices. We already talked about how moving water versus air is a 43% energy savings. Variable speed pumps versus fixed speed pumps is proven that you get at least 17% savings on pumping energy use. In a later bullet, I'll talk about how we apply that to installations, whether residential or commercial. Also, variable speed onboard pump controls are very innovative. For example, if you buy another sensor for the Magna 3 pump, you can control your ground loop on differential temperature instead of constant pressure, so that if I have 10 heat pumps operating and they're putting a lot of load on the ground loop, that pump's going to speed up to maintain, say, a 5-degree delta T across the ground loop. If I have only one heat pump operating, I don't put much load on the ground loop, so it can slow down and just maintain the temperature on the ground loop, which dramatically saves on pumping energy. And it's also very intelligent in that it's not just simply pressure, but it's actually measuring differential temperature, which is variable. You can change it. Once you install it, you can make it 3 degrees, 5 degrees, 8 degrees, whatever works for your application. Now, using supplemental or using water to air units for supplemental cooling within a building, I believe is the best approach, especially variable speed water to air units. So you might have a 200,000 square foot building and it has 12 heat pumps throughout that building to provide supplemental cooling and also perhaps some dehumidification. First of all, you don't have to run the ground loop to all the heat pumps. If you have a radiant floor cooling system, that water is a constant 58 degrees or something similar to that, whether it's 55 or 65, it's perfect as a source fluid for the heat pumps. So the same distribution piping for the radiant system can actually go to the heat pumps as their source fluid. In this example at the right, you have a variable speed water furnace 7 series unit, and the heat pump has a variable speed compressor, but it also has a variable speed flow pump. And the controls within the heat pump will automatically control that pump or a modulating valve. Now, for most applications that most installers are familiar with for a residence, you're used to a FC2 flow center, which is 245 watts for each 2699 pump. The way most contractors hook that up is they hook both flow centers up to the heat pump so that whenever the heat pump turns on, whether it's stage 1 or stage 2, both pumps turn on. But if you do the math, you'll find that for example, a 5-ton unit uses 3 tons of heating or cooling water flow, which is a lot lower. So you can actually use 1 pump when you're on stage 1 and invoke 2 pumps on stage 2. GeoFlow makes a relay that does this automatically for you, so you can buy it from them, or you can buy rib relays and hook it up yourself. But essentially, you're saving 245 watts an hour 87% of the time that heat pump's running, which is very significant. When we look at compressor technology, compressors are 35% more efficient than single speed compressors, especially for really large applications, because most heat pumps in the central plant do not run at full load conditions all the time. They usually run at partial load conditions, just like the 87% example I gave for space heating. Most manufacturers have automatic humidity control. So you can just set the humidity you want the heat pump to maintain. It'll slow down airflow and overcool the coil to get the dehumidification that you need to maintain that set point. And you don't have to do anything. You basically just tell it to maintain the humidity. Another method of controlling flow through the heat pump is if you have a central, say a large Magna 3 for the building and 6 different heat pumps out there, you can put a modulating control valve on the heat pump and set the central pump on constant pressure. And that modulating valve is going to modulate with the compressor requirements, and the main pump is going to maintain pressure. So it's going to slow down or speed up water flow based on how many heat pumps are turned on and operating. And that's an efficient way to save pumping energy. I think I might have gone forward one. Yep. So we're familiar with outdoor reset on boilers. What that basically means is that if you have a really, really cold day, then you have the hottest temperature for your heating system. And if you have a warm day or moderately cold fall day, you have cooler water that's still warm. And that affects the efficiency in a positive way for both boilers and heat pumps, more so with heat pumps, where you can use lower temperature hot water for heating, then you're more efficient. And in general, forced air systems require much higher load side supply water than radiant systems. And if you install the tubing for a radiant system 6 inches on center using 1/2 or 5/8 inch tubing, you get your optimal heat transfer through the floor. And let's say you compare 6 inches on center tubing versus 12 inches on center, your heating capacity is significantly higher with the narrowly spaced tubing. But more importantly, you can provide the same amount of heat at a lower water temperature. So it makes more sense to increase your tubing density, even in heating applications, because it makes the heat pump more efficient in that mode. And you have to put the tubing at 6 inches on center if you're doing radiant cooling. A radiant cooling application does not work very well with 9 or 12 inches on center or with a low mass system. So something like warm board or aluminum fins with tubing sitting directly in a low mass floor doesn't work really well for radiant cooling because it doesn't have the ability to retain cold. Actually, it rejects heat, but you think about retaining cold, that's critical. A typical setback routine for chillers is to make the chiller temperature vary on outdoor air temperature, just like you did a boiler, and that is a mistake. The systems don't work the same way, and the requirements for the chilled water are different. So you either have 2 sources of cold water, one that's above dew point and one that's below dew point for dehumidification, or you make the water temperature the coldest temperature and then you mix it warmer with the thermally conductive structure to prevent condensation. So the rule of thumb is if you're dehumidifying, you want the warmest temperature that's below dew point. So if the dew point is 56.5 degrees, you might use 54 or 53 degree water. And if the dew point is colder than that, then you'd lower the water temperature. If the dew point is 56.5 degrees, you want the coldest temperature to be above your dew point, plus a safety offset. So if the 56.5 degrees is your dew point, you might want to have a 1.5 or 2 degree safety offset just in case the cold water varied coming out of your supply. I will say that in my experience, if you supplied 55 degree water, which is technically below dew point to a large concrete slab, by the time it gets into the slab is above dew point. So having the same supply water as a dew point is not a recommendation, but you can do that. We've found from experience that the high mass of the slab is not heated up as fast just by having colder water. Other algorithms.
Pardon me just a minute, Al. Pardon me for just 1 minute. I want to be respectful of everyone's time. We're right at 1/2 the hour. Al has graciously agreed to stay online, and so you do have your CEU used for the hour. But if you'd like to stay on with Al, he's agreed to stay on as long as there are questions, and I'll be here as well. So go ahead, Al. Sorry about that.
Thanks. Yeah, we have 3 slides, so we'll get to questions very quickly. So some of the algorithms that we use, first use predictive control. If you have an unoccupied space, say overnight, the temperature of the room 60 degrees, it needs to be 72 degrees by 8 a.m. You can use the historical response time of the thermal mass, or ASHRAE has something called optimal start program. This is more for low mass systems. But if you know that when it's very cold outside, it takes an hour for that space to heat up. If the occupancy is 8 a.m., then you would start heating it at 7 a.m. At the same time, it's a moderate temperature outside, it might take a half an hour. Or a high mass system may take 2 or 3 hours to change. And that's different than just simply turning on the heating system 20 minutes before it's occupied. And so using predictive controls for that application works well. The example I gave you with the cathedral in Europe is you pre-cool the space with nighttime air. Like last night it was cold in Colorado, but today we're going to have a cooling requirement in the space. Pre-cooling the conditioned space using outside air is your most efficient way of using the optimal energy source to cool or heat the building. And then for dedicated outdoor air systems, just like boilers or other heat pump applications, having the warmest temperature to meet requirements and cooling mode and vice versa is the highest energy efficiency. And then if I know I'm going to have solar heat gain, such as that lobby in California at 1 or 2 in the afternoon, I actually would want to pre-cool that space when the energy rates are lower, and it would lower my peak demand for that system. ASHRAE is really struggling on 62.1. They're really struggling with ventilation. For the extremes, the original ventilation rates they actually recommended were based on getting rid of body odor. They were talking about indoor air quality, but the tobacco industry shut them down for that in the 1920s. And the predecessor to ASHRAE actually switched gears to be body odor. But then they got around from all ventilation requirements, and COVID completely flipped them upside down because they found that some ventilation rates didn't work based on CO2, especially in small spaces. So in 2022, ASHRAE put out a paper on 62.1, got a $14 million grant from the government to go check this out and figure it out. So they're still working on it, but the bottom line is you want the bare maximum ventilation, especially for a house or residence. One of the things we'll do is we'll undersize the ERV. We do not need a 300 CFM fan in the ERV. If we have the heat pump, like a variable speed heat pump in my house uses 48 watts of power to circulate 300 CFM. So if I simply turn my heat pump to run 24/7 in fan only mode, all I need to do is inject stale air or fresh air into that airflow. And I use the heat pump fan, which is more efficient than the little tiny fan that's in the ERV. And I can use a smaller ERV and still meet the requirements for mechanical ventilation. The third method you want for efficiency is staging your supply. So if you're in cooling mode, you might first look to see with your DDC system, hey, what's the outdoor air temperature? And if it's colder than what you need, then you just open a damper and bring in outside air, assuming the humidity is not a problem like I talked about with Pittsburgh. Second option is maybe do hydronic cooling with the DOAS unit by cooling or heating a fan coil, or use radiant floor cooling in the floor. And you might use radiant floor cooling as your primary, never set it back, and then use the other ones. But the point being, once you have the ability to stage supplies, and then finally with supplemental heat pumps within the spaces, you can actually choose via the software what turns on and when, as long as the architecture supports that. The last point related to efficiency and ground heat exchangers is you want to use the highest efficiency process heat exchanger. So if I have free solar energy for heating, I would use that before I would use a heat pump for heating, or maybe before I use a boiler, or maybe the price of gas is lower and I want to save money, so I'll use a gas boiler before the heat pump. So it's a hybrid system that allows you to do that. But normally you want to use the highest efficiency process, which is seasonal performance factor, for your heat exchanger on the source side, and also on the load side. If you have a direct use of fluids like we talked about, using that on the source load side dramatically improves your efficiency of the heating and cooling system. If you control the source entering water temperature for water source heat pumps, that's another way of gaining efficiency. If I have a solar array and I'm in heating mode and I can boost the temperature of the water going into the source side, that would be optimal. And then I talked about segmenting a ground heat exchanger with solar thermal arrays allows you to downsize the tank size. And for heating dominated clients, you can supercharge the ground loop in the summer. The last thing I'll talk about is I often see designs where the hot water supply to the building and the chilled water supply to the building are mixed to provide the right temperature in the radiant floor. That's really a mistake because I'm paying to heat hot water and paying to chill cold water, and I'm mixing the two together to make lower water temperature for heating or higher water temperature and cooling. If you simply mix the supply and return from the radiant floor, you achieve the same thing without losing that energy. So if I'm in heating mode, the water goes to the radiant floor, it comes back cooler. So I just mix enough cold water to keep the radiant floor temperature and the hot temperature and vice versa for cooling. So when you put this all together, it looks something like this. You got kind of a heat pump in the center with either a ground heat exchanger or a source side heat exchanger. It could be district water, chilling, cooling tower, solar thermal boiler. We don't really care. If the piping's in place and we have controls to measure the temperature of these devices, we can calculate energy efficiency in real time and select the most efficient source fluid for whatever we're doing. If you get to the heat pump, I can either put it through the heat pump if I need to change the temperature of the water, or the blue and red line on the bottom. I can use passive radiant cooling and heating and basically use fluids directly into thermal storage, which is either a tank or a circulation and fluid, and circulate that in my radiant floor system. Once I have that heating and cooling system operating, the only other thing I have to consider is how do I condition the air? And that's ventilation, and then also supplemental cooling to maintain dehumidification. And that uses energy recovery or DOAS unit with hydronic fan coils, since I already have cold and hot water is centric to my system. And on the far left, what we found as an installer for 15 years is it really got too complicated to put a DDC system into a residence, because you really can't maintain that with your average contractor that's used to dealing with 24-volt thermostat. So unless you have a commercial building that already has a DDC system, the controls for this are much more complicated than it needs to be for a residential structure. So let's go back 13 years ago, and this is the design our company came up with when we applied for some patents that essentially allow any fluid to move from any source, which is the lower right side here, ground heat exchanger, process heat exchangers, into a system and go to a hydronic system. And then you have dehumidification or ventilation with an ERV. And this architecture right here is one of the most common architecture with most state-of-the-art buildings today, in that it allows you a lot of flexibility at the same time, on top of an energy efficient building envelope, gets you to net zero performance. So if you want to get a copy of this presentation downloaded, you go to tinyurl.com, 6 Charlie Tango 4 Papa Juliet Sam, 6 CT 4 PJS on the top. If you want to get a lot more information on how the technology works and how you actually build the system, you can look up any one of those patents on the bottom under Google Patents, and you can read the specification. The specification is the same for the patents. So if you read the 20 pages or so of specification, it describes why the technology works like it works and how to put it all together. And with that, I would just simply say that if you are thinking of designing a building like this, we work well with engineers and designers to help you get over the hurdle of just the net zero part of this, and then you do the rest of the design that you need for your building.